So in the previous video, we talked about Newton's first law. So Newton had quite a bit of laws. So he was a very great scientist that contributed to science. So now let's talk about the second law. So in Newton's second law, which is also the law of acceleration, what essentially Newton is saying is that a force produces an acceleration. So if an object is, let's say, sitting on a table, let's say your phone is on a table, if you apply a force on that phone is going to move. If you apply more force, that phone is going to move even faster. Okay. So if you're applying a force with one hand, you see your phone is going to move. And if you apply it with two hands, you see it will move even faster because you've applied twice the force. And so twice the force will produce much more acceleration. Remember, acceleration is change in speed or increased speed. If you're driving at 30 miles per hour and you move from 30 miles per hour to 35, that's an acceleration, an increased speed. So what that law essentially says is the acceleration produced by a net force on an object is directly proportional to the net force. What that means is if you have more force, you have more acceleration. And remember, force is a vector. So if force is being applied on an object, the acceleration is going to be in the same direction as the net force. So if you're applying it to the right, the object is going to accelerate to the right. If you're applying it to the left, the object is going to accelerate to the left because force and acceleration are both vectors, which means they have magnitude and direction. So the force is going to always act in a certain direction, and it's that same direction that the acceleration is going to be produced. Is going to be produced. And so the force is directly proportional to the acceleration, but it is inversely proportional to the mass. What is inverse proportionality? Inverse proportionality means that if one one parameter is increasing, the other one needs to be decreasing. In this case, let's compare force and mass. If you have more force, let's say if you have, now let me say mass, because mass is one object that you can easily visualize. Let's say if you have a very large object, applying a force on that large object is not going to produce as much acceleration as a small mass object. And so if you see large mass, right, will mean that it needs more force. Okay? More force will need more force will be needed to accelerate a very large mass object, and a small force will be needed to accelerate a small mass object. Okay, but with acceleration, right, you see that acceleration is going to be much higher for a small object than for a large mass object. That's why acceleration is kind of inversely proportional to the mass. And so the formula for Newton's second law says that acceleration is equal to the net force divided by the mass. So this one here is one thing you really need to pay attention to. Acceleration is equal to force divided by the mass. So a small net force, okay, acting on a large mass is going to produce a small acceleration. A small net force acting on a large mass is going to produce a small acceleration. So if you look at it, small force, small acceleration, they go together. That's why they are directly proportional. But look at mass, large, small acceleration. They go in different direction. When the mass is large, the acceleration is going to be small. But if you have a large net force acting on a small mass, it gives you a large acceleration. You see, large for force, large for acceleration, they go together. That's direct proportionality. But when the mass is small, the acceleration is large. That's inverse proportionality. They go in different directions. So let's check this. Consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart decreases to half the acceleration of the cart, obviously. Remember, mass and acceleration, they go in opposite direction. Okay? So if you have the mass, obviously the acceleration is going to double because they go in different direction. They're opposite. If you push a cart along a track, so twice as much net force acts upon it. If the acceleration remains the same, what is a reasonable explanation? So if when you look at the force, if you double the force, right, and the acceleration does not change, it means that the mass was probably doubled also, because mass and acceleration are directly proportional. So the mass of the car doubled when the force was doubled. So here now let's talk about acceleration g, which is free fall. We've been talking about free fall, and we've said that an object is in a state of free fall if the only force acting on it is gravity, so neglecting air resistance. So if the only force acting on an object or on a falling object is gravity, then that object is in a state of free fall. And we've said that on Earth, remember, on Earth, an object in free fall accelerates towards the Earth at 10 meters per second. That value is constant. That's why we said earlier that a 1 kilogram object has a weight of 10 Newton, and that's because you multiply that mass times this value, 10 meters per second square. You multiply that, that's how you get the 10 Newton, because this value is constant for every object. So if weight is the only force acting on an object, then that object is going to be accelerated towards the earth at 10 meters per second square. And that's a constant value. It is also called the acceleration due to gravity. Okay? The G value. It's called the G value. So at one instant, an object in free fall has a speed of 40 meters per second. Its speed 1 second later is, this is something we've seen before. The speed 1 second, we assume the object is falling downward. Assume the object is falling downward. Because if that object is in a state of free fall, right, it means that the object is going to be accelerated at a value of 10 meters per second square. And so 1 second later, the object is going to be accelerated at a value of 10 meters per second squared. So that's why you add the 10 to the 40 to give you that 50. That's going to be the acceleration of the object, because the only force acting on it is the weight. So this is another scenario. Again, remember that the value for g on Earth, which is the acceleration due to gravity, is 10 meters per second squared. That is the acceleration, that's the free fall acceleration. And twice the force will produce twice the acceleration. But if you have twice the force and twice the mass, it is going to produce no effect. It will produce no effect, because those two will cancel out, as you can see. Let's say you double the force, it becomes 2 force divided by, you double the mass, it becomes 2m, right? 2f divided by 2m, you see the 2 will cancel one another, and it still gives you g that you had initially, because force and mass are directly proportional. So if anything happens to mass and that same thing happens to force, it will produce no effect. So you have a 5 kilogram ball and a 10 kilogram iron ball are dropped from rest from negligible air resistance. The acceleration of the heavier ball will be Look at the masses. One is as twice as the other one. So remember, it is weight, okay? Because it is weight, the acceleration due to gravity on them will be the same. The acceleration due to gravity will be the same. It doesn't matter the weight. The acceleration due to gravity is the same for every object that is under the influence of gravity alone. And that value is 10 meters per second squared. It's the same for every object. So you have a 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest when the free falling 5 kilogram iron ball reaches a speed of 10 meters per second. The speed of the free falling 10 kilogram ball is, again, is the same thing. Okay, 10 meters per second squared. Same thing. So the whole idea behind those questions, the whole idea here is for you to understand that when an object is acting under the influence of gravity alone, right, it is going to be accelerated at the same value. It will be accelerated at the same value, irrespective of the mass. When the acceleration, the ratio of the weight to the mass is the same for all falling objects in the same locality. The acceleration are the same in the absence of air resistance. We've talked about this before. Because when the mass become big, guess what? The force also is going to increase. And so for that reason, G remains the same. So the G for a leaf and the G for a stone is going to be the same. Take note. Demonstration of a feather and a coin in a vacuum. In a vacuum, a feather and a coin fall together at G, the acceleration due to gravity. So these two objects were dropped in a vacuum. Again, a vacuum is an environment in which there's no air. So dropping these two in a vacuum, the realizer, both the coin and the feather, they all accelerate at the same value. As you can see, they are all at the same level. So irrespective of your mass, G for both objects is the same. When air-filled glass tube containing a coin and a feather is inverted, the coin falls quickly to the bottom of the tube while the feather flutters to the bottom. A situation to ponder. Think about it. When an air-filled glass tube containing a coin and a feather is inverted, the coin falls quickly to the bottom of the tube while the feather flutters. Now, in this case, the only force acting on those objects is not gravity because there is air inside. So there is air resistance. So this air resistance is going to act on the feather more than the coin because remember the feather is kind of light and it has a bigger volume than the coin, and because the coin has more mass, right, inertia comes into place now. Okay, when the air is removed by a vacuum pump and the activity is repeated again, when the air is removed, now the both objects are acting under the influence of gravity. And so both the coin and the feather drop together side by side because they are all accelerated at the same value. So we've probably talked about someone using a parachute, right? When you use a parachute, uh, what keeps you up? What keeps you up is the fact that the air resistance of your parachute is balancing your weight. So this is known free fall. It's known free fall. So when you're using a parachute, that is not an example of free fall. We've talked about that before because you have air resistance acting up while your weight is acting down. So you have a force due to gravity acting downward, and you have air resistance acting upward. So again, this is not an example of a free falling object when you're flying a parachute. When a 20 Newton falling object encounters 5 Newton of air resistance, its acceleration of fall is less than g. Okay, when I have a 20 Newton falling object that encounters a 5 Newton of air resistance, obviously the 5 Newton is coming to reduce the 20 Newton because they act in opposite direction. So remember, the weight acts downward and the air resistance act upward. So the net force is going to be 20 Newton minus 5 Newton. And so because of that, the weight is the object is going to have less g, because remember, g is fully established, or is going to be 10 when there's no air resistance. There's no air resistance. There's no force that is reducing the weight. So when acceleration is less than g, known free falling object. Those are known free falling objects because air resistance is acting on those objects. As object as falling object gains speed, force exerted by surrounding air increases. The force of air resistance may continue to increase until it equals the weight. At this point, net force is zero and no further acceleration. At this point, no net force. When when the air resistance increases until it balances the weight, we said the object has reached terminal velocity. When you see an object that has a weight that is being balanced by the air resistance, we say that the object has reached terminal velocity. So terminal velocity is a point where the velocity becomes constant, no acceleration, because the weight is now balanced by the air resistance. So if you have a 50 Newton person, is to fall at terminal speed. What does terminal speed mean? It simply means that air resistance balances the weight, right? So for that reason, if it is at terminal speed and the weight of the person is 50 Newton, then the air resistance will be 50 Newton. Okay. So at terminal speed, that object is in a state of equilibrium, no acceleration. You have a skydiver falls faster and faster through the air. What is air resistance doing? When this object is flying faster and faster, air resistance should be increasing. And air resistance will increase up to a certain point when it is going to balance the weight of of the person. When the object's weight is being balanced by the air resistance, then this person will no more increasing speed. The speed is going to be constant, no acceleration. Have a skydiver continues to fall faster and faster through the air. What is the net force? Of course, the net force is actually decreasing. Okay, so if it is going faster and faster, what happens? Because the air resistance is increasing. Remember, air resistance is acting in opposite direction to the weight. So because air resistance is increasing, it is reducing the net force. Again, what is the net force here? Gravity. I mean, not that the net force is gravity. The force acting in opposite direction is gravity, and the air resistance is acting in the other direction. So if air resistance is increasing, it is going to be decreasing the weight that is acting downward, thereby making the net force to be decreasing. Skydiver continues to fall faster and faster through the air. Obviously, acceleration decreases. Now you consider a heavy and light person with same size parachute jumping together from the same altitude. Who will reach the ground first? Who is going to reach the ground first? The heavy person. A heavier person has a greater terminal velocity. Do you know why? Think about it. The person has a greater terminal velocity. Remember, in this case, right? In this case, you cannot talk about them reaching the ground at the same time because they are not free falling. It's only when objects are free falling that they will reach the ground at the same time. But in this case, remember, they are not free falling. The objects are not free falling. They are not. And because they are not free falling, they cannot reach the ground at the same time. And so the person with a heavier that's heavier is going to have a greater terminal velocity because it has more weight. So it is going to keep accelerating faster than the person with a smaller weight until a point when it reaches terminal velocity. All right, so this brings us to the end of this presentation, and that was that for Newton's second law.